all for your participation today here. I would like to thank you all for participating in the series of webinars that we are organizing with ENTRUST project. The big title of the series of the webinars is Trust or Bust, reinforcing the IoT interoperable security stack with efficient secure lifecycle management capabilities, giving emphasis on RISC-V opportunities that come up for the projects. So we stand for on our last webinar, the third day in a row, that elaborates with the compositional verification and validation of toolchain for design time system accuracies. I would like to thank the speakers who are going to participate today. Stelios Basagiannis from Collins, along with Simone Flavio Rollini, and sorry, give me 1 second for some admissions that run. Okay, great. Sorry for this one. Minute, and also Leonard Tudoras from ENTRUST projects. Actually, we take pride in this collaboration, since we have the opportunity to have long discussions and give a series of webinars that can cover the cybersecurity aspects, I would say more holistically, for end-to-end applications, and from the experience that we have gained from several use cases. In REWIRE, we elaborate with smart satellites, smart cities, and smart automotive use cases, while ENTRUST also has extended experience from real-world implications in health IoT ecosystem. So we are very glad to be able to organize this session, but let me not, let's say, spending more time on this one. I'll explain a little bit the flow. So right now I'm going to give the flow for a short introduction to Sofianna Menesidou, member of our technical coordination team in REWIRE, to give a brief introduction and talk about the vision towards trustworthy system of systems. So Sofianna is going to take the floor, and afterwards we are going to continue with the main session performed by our partners in REWIRE and the Trust project, Collins and TUE. So Sofianna, you can take the floor for a brief introduction.
Thank you, Thanassis. Let me share my screen. So hello also from my side. In the following presentation, I will give you a short introduction on both REWIRE and Trust projects and set the scene of what will be the focus of this webinar. So in the context of the entire compute continuum, which means that there is a service graph chain consisting of multiple heterogeneous devices, there is a need to enhance the trust. Until now in the literature, most works focus on enhancing the security profile of a device, but they are focusing on the integrity part. However, getting closer to what has been defined in the standards regarding the trust and the trustworthiness of the system, it's not only what is related to its integrity, but covers a wide gamut of properties such as reliability, safety, dependability, and so forth. When it comes to the concept of trust, this comes to two flavors. One flavor has to do with any type of data source, which is the device. So this is called node-centered trust. And then we also need to be able to safeguard the trustworthiness of the communications and associate the trust level on the actual messages to be exchanged. This is what we call the data-centered trust. So by combining the data-centered trust with the node-centered trust, this is what allows us to characterize the trust level of a device, and then based on this we can characterize the entire service graph chain or the entire domain of multiple service graph chains. The common denominator to do such trust characterization is to have access on the evidence based on which we can assess the trust level of such devices in a verifiable manner. For instance, when we don't trust the evidence and have a lot of uncertainty on our characterization of trust level, we need a rich set of mechanisms to support the secure lifecycle management of the devices, starting from the design phase that allows the device to be equipped with all the appropriate tools, to the runtime trust assessment for establishing its trust level, and all the way to establish its trust level if something goes wrong. REWIRE and ENTRUST offer protection mechanisms supported by a wide range of different underlying hardware-assisted root of trust, based on which we can characterize the trust level of the entrusted part of the software being instantiated in both devices. However, there are some important challenges that we need first to cover. One important thing when we are trying to characterize the trust level of the device is we either rely on his evidence or on the evidence of the adjacent devices. In this case, we could have contradicting data. Thus, there is quite a lot of techniques in the literature considering probabilistic logic, such as the surjective or fuzzy logic, that can cope with this type of contradicted evidence, and this is the assumptions we made in REWIRE, that there is existence of such tools and capabilities, while in ENTRUST we offer such trust assessment mechanisms based on surjective logic. And another important thing that in this concept is the concept of verifiable evidence, and is what type of evidence we need to monitor that will not kill the device in terms of overhead, but are also rich enough to be able to allow the accurate trust assessment. Remote attestation mechanisms can be used to provide such verifiable evidence, but the challenge here is what type of properties we need to attest, or what is the design space of those properties that if I attest them, I can actually have guarantees that my device is operating within the expected boundaries. In many of the existing works, they actually assume that someone defined these properties, or they are trying to attest the entire software stack, which is impossible because the overhead imposed on the target device will disrupt the operation of the device. Our vision in both projects is to converge the trust with safety, so as to disturb the normal behavior of the so as not to disturb the normal behavior of the system by adding resource-heavy security controls. Here we highlight very briefly the objectives of the two projects towards building a continuum of trust. In a REWIRE project provides enhanced operational assurance by assessing device configuration and execution state, trustworthiness sources such as attestation and misbehavior detection mechanisms, trust assessment enablers, new crypto primitives and protocols for secure and privacy-preserving exchange of trustworthiness evidence, security by design through formally verified software and hardware co-designs, and risk assessment mechanisms. On the other hand, the trust focuses on medical devices and provides trust assessment enablers, attestation-based trustworthiness sources, advanced trusted computing capabilities for safeguarding the entire life cycle of CMDs, new crypto primitives and protocols for the secure and privacy-preserving exchange of trustworthiness evidence, conformity assessment and certification standards, risk assessment, and security by design through formally verified protocols and designs. As we can see, there are several common objectives in the two projects, and also both projects are complementary, and they have the common denominator of how to use the formal verification for identifying the design time assurances. Here we list the operational phases of the REWIRE and ENTRUST. On the left is REWIRE project, and on the right is the ENTRUST. What is important here is that we are trying to merge the benefits of design time formal verification mechanisms with runtime trusted computing capabilities. As already said, both projects have runtime phase for the device onboarding, the trust assessment, and the trust reestablishment, and the design phase. In the design phase, both projects use formal verification for identifying the design time assurances of what we can model and bootstrap the trust of the device. In many cases, we cannot model everything when it comes to protocols because the models are complex and it cannot basically solve on time. So we need to make some abstractions. What we have showcased in both projects is that whatever we abstract is essentially what is needed to attest during runtime, because they are the only properties that which don't have the necessary design time assurances that they behave as expected. So we are limiting the space for the evidence that need to be modeled during the runtime, and such evidence is enough to allow us to characterize the trust level of the devices. So that's all from my side. Now I give the floor to Simona and Stelios for presenting the compositional verification and validation capabilities of REWIRE.
Thank you, Sofianna. Probably Simona can share his screen. Yes. Okay. So, hello everyone. My name is Stelios Basadianis, and together with my colleague Simona Fluvio, so-called applying formal verification techniques at the design time for cybersecurity properties. And starting a little bit for the introduction, for those who are not familiar with formal methods, we are talking about mathematical reasoning techniques that we pretty much try at design time to build models representing the real system and try to verify the state space generated out of these models in order to provide assurances that certain properties will hold. Obviously, when we are discussing about cybersecurity in a system of system context, there are lots of different engineers involved into each separate, let's say, phase of the development of a complex system, right? So what we've been looking into REWIRE was, okay, the requirements that we need to fulfill, the overarching so-called requirement for a particular device or a system that is comprised of several devices. Try pretty much to trace all of these requirements in the different levels of module development for a particular device. Module meaning that the device will have a software, let's say, functionality, but also it will be based on some hardware, let's say, implementations down at the low level of the device. So the question becomes, okay, if we have an overarching property, our system is safe or secure, how can we provide evidence for that this property is holding in all of these different steps? And this is where REWIRE comes, and this is pretty much employing a different series of very known formal methods tools, starting from theory improving down to the low-level microarchitecture at the hardware side, where, for example, we've showcased that an AES coprocessor is functionally correct in order to implement its specific instructions. We prove this, we take the evidence, and then we try in a compositional manner to argue that whether a software component is going to utilize, let's say, a hardware, let's say, based crypto system, then this software with this hardware will be obviously, this instruction will be obviously correct, and this software interacting with this hardware will also be correct. And in a bottom-up manner, we try to build this evidence in order to trace those security properties. So if you go to the next slide, thanks, Simona. So this is a picture of the complete architecture of the REWIRE framework. And on the left side, you could see what are the different tools that we have employed in order to provide this evidence from a requirements point of view. Let me just mention that those evidence are critical to certify our products, and when coming from, for example, an automotive or an aerospace domain, we need certification guarantees to be at place, especially for especially for cases that security and safety are too tightly connected properties that pretty much protect safety critical systems. So starting with SAIL and CAVA frameworks down at the hardware level, at the instruction set level, using theory improving, the COC theory improving, we try to prove an instance of the AES module. At the same time, we've employed model checking, the new XMV, and software model checkers like the CBMC pretty much to provide additional guarantees for software implementation of several, let's say, solutions like the LRBC algorithm, which is a side channel attack protection solution. developed by one of our partners. And at the same time, we've also used additional tools like, for example, Verifpal, in order to verify the attestation protocol for properties that we couldn't, for properties that relates to the attestation agents triggering the attestation. Important to understand and distinguish that not everything can be formally verified in the models can generate enormous state spaces. That said, we offering these solutions at a design time, but as Sofianna mentioned, the properties that we cannot verify, those are the properties that attestation is triggering in order to offer the security solution in as much comprehensive as possible or holistic as possible, from the design time with formal methods, using attestation and other REWIRE features at runtime. So let me take it to my colleague Simone, who is leading the formal verification from our side with more information.
Thank you, Stelios. Can you hear me fine?
Yes.
Very good. All right, I'll move then to the two main technical topics of this talk. One is about modeling and verification of the specification and implementation of a leakage-resistant mode of operation. By leakage-resistant mode of operation, I mean a method for using a block cipher. This is a cryptographic algorithm intended for fixed side blocks of plain text, resistant to leakage in such a way that confidentiality and integrity of data are preserved. The second topic is about modeling and verification of the specification, in this case, of an attestation protocol, which is a security protocol whose aim is to verify the integrity of a device state which is located remote. Let's start with the leakage-resistant mode of operation. Now, the first important aspect to understand when one wants to model and verify an algorithm is the use of a specific formal language. How can we choose which formal language to use? In the language we chose and applied in this case is SMV and its extensions new XMV and new SMV. The language dates original back to the 90s and has been later extended and developed to model transition systems and properties of different kinds. For example, properties that can be represented by temporal logic at the Fondazione Bruno Kessler here in Italy. The two properties that we use here to characterize the functional correctness of the specification we intend to model are the correspondence of encoding and decoding, which is what I mean by encoding and decoding integration. That is, after a plain text has been encoded and the decoding function is applied, then the original text is preserved. And also the tag generation verification correspondence in absence of attacks by an adversary or abnormal conditions. The tag generation verification is a pair of functions that is typically used to ensure authenticity and integrity of data, for example, in message authentication calls. One important element that allowed us to successfully perform verification is the use of a technique very widespread in the field of formal verification that is called abstraction. This is a soundness preserving abstraction. What does it mean? That if we take out and abstract away a component from our model, then we obtain another model such that if the property that we want to prove shows to be valid in the abstracted model, then it is still valid in the original model. The goal is to simplify the model from a verification perspective in such a way that we preserve the validity of the results that we get from the verification, at least when a property is declared valid. This is to give you an idea of how an encoding looks like in the SNV language. Let's take a quick look. So we have two main routines in the LARVC2 mode of operation, one for encoding, the other one for decoding. The mode of operation is a composition of functions that we can see, for example, by the use of KDF and MEN functions and TGF, tag generation function, and tag verification function. The mode of operation is parametric. In the block cipher, that is the encryption function that is used to encrypt and decrypt blocks of data. In particular, in this encoding, we're using AES with 128 bits. Also, the key, 256 bits, and once 128 bits, and a variable number of blocks that correspond to a sequence of blocks of the plain text or the ciphertext, depending on whether we are encoding or decoding. The reason we use SNV for this particular verification effort is because these kind of algorithms are heavily relying on fixed white unsigned integers that translate to very specific data structure in formal languages. And SNV, with respect to its competitors in the field of formal verification, have a very solid and proven by means of papers and reported experiments capability of handling fixed width unsigned integers. We have the two properties which we are verifying. The first one is the correspondence of the tag generation and tag verification functions. And the second one is the correspondence of the encryption and decryption mechanisms, such as when we decrypt a message that was previously encrypted, we get the original message. As you probably got an idea by seeing the sheer amount of bits that corresponds to the input size, which is to be taken to the power of 2 when we consider the search space that we need to examine in order to perform exhaustive verification by means of model checking, which is the method we are using here, you won't find strange that, let's say, scalability is an issue for this kind of verification activities. In particular, the verification task can be split into two parts. One corresponds to the initialization phase, and the second one to the solving phase. The initialization phase is about taking the models and translating them into a formal intermediate representation onto which a chosen verification technique is applied to perform solving itself. The difficulty here is definitely the size of the intermediate representation, which can be seen by taking a look at the thresholds, the time that was reached in performing the translation of the original model into the intermediate representation. We are considering here a machine with 64 gigabytes of RAM in terms of memory threshold. Well, in order to assess scalability in a more thorough and progressive way, we took into account 3 different verification settings. One, where you see XOR in the block cipher column, corresponds to a first assessment where the block cipher, that is the function used to encrypt and decrypt the blocks of information, corresponds to a simple XOR operation, which has, whatever is needed to be a block cipher, but it's the most trivial you can think of in practice. The second one is the use of the standard in industry, that is the ES algorithm, and we developed our own encoding in the SNV language of AES, but definitely, the two couldn't scale. The best results are the ones we achieved by using abstraction techniques. And in particular, we were able to prove the validity of the 2 properties in our SNV encoding by using 1 and 2 blocks of plain text, but then again, we reached a memory out situation. We ran into a memory out situation when we tried to scale up to 3 blocks. Just a second, we can go back to the encoding to give you an idea of what an abstraction means in terms of SMD. So on the top, you can see 2 declarations of AES, one with 256 bits, one with 128 bits. In this sense, abstraction means to replace the actual encoding on the AES function with a declaration of the signature, which just says that you are taking 2 inputs, for example, 256 and 128 bits, and we output as a result 128 bits. So the actual function is stripped out to its bare minimum of being a signature, which gives you a specification of what the inputs and the output are. So after verifying the specification, the next task would be to verify the implementation based on this specification. That is, to verify whether the implementation would deviate significantly from the specification. For this aim, we proceeded in a very similar fashion. That is, we consider 2 properties of correspondence of tag generation and verification, and the integration of the encoding and the decoding routines. And we also took into account 3 verification settings: the original implementation in C as provided by our partners, an implementation where the block cipher, which originally would be a full implementation of the AES algorithm, would be replaced by a minimal XOR, and also the implementation with a block cipher being abstracted again by means of an interpreted function. For this activity, we relied on the CBNC model checker, which is widely adopted in the verification community, is still under active development, and has always shown good performance at the software verification competition, which were held more or less yearly, and also has a clean interface, and most importantly, for what we are performing here, allows the user to perform abstraction by means of uninterpreted functions. This is exactly what we wanted to apply here as a verification method. Since the use of an actual programming language adds another layer of difficulty to the verification tasks, we also split the verification activity into several steps with different degrees of difficulty for the tool by progressively constraining the input domain of the inputs of the mode of operation algorithm. Another point which I haven't previously mentioned is that when performing model checking, you can use either SAT or SMT-based techniques. What does it mean? Now, in SAT, you encode your whole problem into Boolean logic, with the risk of seeing the problem growing enormously in terms of the size of its representation. SMT has a more sophisticated encoding because it can directly reason, for example, on data structures that allow to represent fixed with unsigned integers natively, on arrays, also on interpreted functions, as we have mentioned. On the side of SMT, it's more difficult for the tools to reason by combining these theories than for a tool to perform reasoning just in the Boolean world. But then again, it's a compromise that one needs to take into account when performing formal verification. This is to give you an idea of how the introduction of simplifications and abstractions look like in a piece of C code. On the left-hand side, we have the declaration of an uninterpreted function which represents and abstracts the AES algorithm. In the center, we have the use of XOR to simplify the AES function. And then on the right, it gives you an idea of the amount of not so much instrumentation that needs to be done in the code in order to perform verification by using these kind of simplifications and abstractions. Also, as previously mentioned, we perform verification by progressively constraining the input. From the bottom to the top, we have no constraints to the key, to the nuance, to the plain text and ciphertext, constraining of key and nuance, and constraining of key nuance and also plain text. And this is actually to assess scalability in an iterative fashion. In terms of results, well, we get actually what we expected, at least in terms of verification time, in the sense that when using abstraction at the top, the verification time was the lowest. When using the XOR with the various attempts at constraining the input, we have mixed results. When using the full C implementation of the EES encryption algorithm, there was only one case where the tools we applied were able to prove the validity of one of the two properties, actually. What you see in the solver column are the names of different SAT and SMT solvers that were used in conjunction with the CBMC model checker that we adopt to perform a formal verification. An interesting point, which is actually a difference from what we saw in the case of the SMD encoding and the verification, is that the use of abstraction here, and this might depend on the way the C code is translated into intermediate representation down to logic when performing verification, is the fact that, again, abstraction would result in counterexamples. Now, we talk about abstraction being sound in the sense that if a property is declared valid by the tool, it means that the original code, which has not undergone abstraction, in the original code, the property is valid as well. But then again, abstraction could introduce additional behaviors to the program which has undergone abstraction, and these additional behaviors would result in counterexamples that are called spurious counterexamples when they don't correspond to actual execution traces of the original code but were introduced because of abstraction. And this is a significant and interesting difference with what we saw for the specification in SMD and the verification by means of the new XMD tool. On top of proving functional correctness of the implementation with respect to the specification, the use of tools such as CBMC allows us to easily examine and detect the presence of memory safety issues, undefined behaviors, and other typical issues that are strictly related to the fact that we are using a real programming language such as C. We actually identified a few issues that we are going to see in a moment and reported them to UCL, to our partners in REWIRE. And for each issue, they either fix it or justified it. And that's the typical, let's say, flow of verification and implementation that you would like to have in industry, in the sense that there is a development team which takes care of developing the code, and the verification team which analyzes the code and gives information back to the development team, which can then improve the code. In terms of what kind of undefined behaviors and memory safety issues we can take into account, for example, array bounds analysis, time casting issue, division by zero, floating point overflows, integer overflows, endpoint arithmetic, and undefined shift. These kind of things that are all offered by the use of tools such as CBMC. Now, what you can see at the bottom is one of the elements of the issues that we reported back to our own partners after performing verification. Verification is performed in a structured way where we set up a so-called proof harness file for each relevant function, similar to what you would do in the case of test harnessing, both in isolation and in the context where the functions are called, and then you perform a verification. Few tables to give you an idea of the results that we obtained. I think the key point here is to highlight that we detected a few cases of arithmetic overflow that you can see reported here in a more or less formal representation in the central table. And for each of these overflow occurrences that were returned by the model checker in form of a counterexample execution traces, we gathered evidence of a falsification of the property under account and the specification of the input assignments leading to this falsification. We created for each execution trace a counterexample harness, so-called, to be given to developers to examine the finding, investigate it, and replicating the issues we got by means of formal verification. The second topic, which I'll cover more quickly, because it is still ongoing work, is about modeling verification of a security protocol. The target here is an attestation protocol, as we said, to verify the integrity of a remotely located device state, with the additional property of being able to perform zero-knowledge attestation without disclosing information on the device state. On the right-hand side, you can see part of the semi-formal representation and coding of a portion of the attestation protocol, which consists of two phases. One is called join, one runtime attestation. On the right-hand side, you can see the join phase. When it comes to deciding which language to use for protocol verification, we need to take into account characteristics such as the expressivity, soundness, completeness, and termination. What do I mean by that? In general, these problems are definitely difficult, and this results in general undecidability, which means that it's not always possible to find an answer or to have an algorithm terminate in presence of these problems. In general, the algorithm is unsound, so that if a tool implementing a certain algorithm states the property is valid, then it is valid, but not necessarily complete, because also the use of abstraction techniques, so that an algorithm might terminate with a don't know answer. In terms of expressivity, algorithms might be more or less sophisticated in allowing to model different kinds of properties and security primitives. The tools that we considered for the efforts are Proverif, Tamarin, which are the two main tools in the academic world, but a newer also ones that's in the end what we choose to adopt. That is called VerifPal. So why VerifPal? Because it allows the user to have an encoding which is extremely close to an actual semi-formal or informal representation of a security protocol. It is easy to read and to write, as we'll see in a moment. The output is understandable because very often is also difficult in terms of properties, security property is reported as being violated, to find out why exactly happened. So what kind of actions an attacker performed in order to allow a property such as confidentiality or authenticity, for example, to be violated. It offers the modeler built-in security properties that are the kind of properties that you would typically employ in a security protocol: symmetric, asymmetric encryption, MAC key derivation, digital signature, secret sharing, this kind of primitive operations, and also allows automatic translation to the Proverif, the language we just mentioned, and also COC, a tool for theorem proving, so that people or developers or anyway scholars who are more mathematically oriented can perform a deeper verification whenever needed if they feel they need to do so. This is just to give you an idea of how close the language offered by the VerifPal framework is to an actual representation of a security protocol. On the left-hand side, you have the VerifPal encoding. On the right-hand side, you have the semi-formal definition, specification of a security protocol under account. And you can see there is actually a step-by-step match between the two, which is useful both for people who perform the protocol encoding and also for people to perform the verification. And it's also very easy to check at the very beginning whether there is any discrepancy between the actual protocol and its formal encoding. The setting is the so-called Dolev-Yao standard 1. We have a single public channel where concurrent agents exchange messages. We consider cryptographic primitives to be perfect in the sense that we don't care about their implementation, we only care about their theoretical behavior. The VerifPal framework offers two different attacker modes. One is passive for a first assessment. In this setting or mode, the attacker can read, observe the message which are passing by through the channel exchange between the agents and can use them to deduce new information or create new data, but cannot modify them. The active, on the other side, the active mode is the setting where the attacker has plenty of freedom in that it can be able to inject messages, modify, delete traveling messages, can remember data across multiple sessions because the attacker, in order to derive more information, is also able to run multiple sessions of the same protocol in parallel. An interesting feature that we're exploring right now is the possibility to introduce leakage, in the sense that in general, the data private to an agent, so locally derived, stays private. But it is possible to assess what is the impact of the security protocol in case a particular piece of data is being leaked to the attacker. And also, in order to find, let's say, intermediate settings between the passive and the active attacker modes, it's also possible to label some of the messages which are being exchanged as guarded, in that they can be read by the attacker but cannot be modified. So the first batch of analysis we performed on the join phase of this attestation protocol focused on the confidentiality property. We wanted to check whether it would be possible for a passive or an active attacker to derive sensitive data despite of the security mechanisms in place. So we first consider a scenario where there is a simple passive attacker and all the messages are unguarded. And then we focus on the active attacker with multiple scenarios. So all messages guarded, which means that, again, the attacker could observe, read all messages being exchanged between the agents, but not modify any of them. All messages guarded except for a single one. And then again, this is something that we do typically when you want to assess the scalability, of the analysis, because the more freedom the attacker has, the more difficult it is for the verification algorithms to scale. So first, all messages guarded, then all messages guarded except one, then all messages guarded except a, let's say, sub-channel. So just focusing on an exchange of information between the two agents chosen among the various agents in the protocol, and then all messages unguarded. So the results, let's say, determine the threshold of scalability of the tool, at least for this protocol. in fact, when it comes to the passive attacker and active attacker with guarded messages and guarded except a single one, let's say scalability was handled pretty nicely by the Verify tool. But then when we moved to considering free actions of an active attacker on a sub-channel for totally, completely unguarded messages, then the tool was not able to scale. And the next steps here are to consider an extended version of the protocol encoding that we analyzed and to perform confidentiality and authenticity analysis, and also take into account leakage, which seems to be a very interesting point to take into account.
Thank you very much, Simone. I have exceeded a little bit the time, but we are still on the time schedule. Before we continue with Leonard's presentation, I would like to ask if there is one, let's say, probably quick question that someone would like to pose before we proceed. And we are going to leave time also at the end of today's webinar for questions to all the speakers. No, so I think, Leonard, you can proceed with your presentation.
Thank you very much. Let me share my screen. So, hello everyone. My name is Leonardo Doraki. I'm a third-year PhD candidate at Iowa University of Technology, and I'm working on the formal verification component of the ENTRUST project. During today's presentation, I will give you some context. I will discuss a bit about formal verification of security protocols, domain-specific language for protocol verification, as well as runtime verification, and I will give you an update on the current status and the next steps. As you might already be accustomed with our project, the main challenges are security and privacy concerns, the heterogeneous and complex device environment from various vendors in the connected medical devices ecosystem, and also challenges to provide manufacturers with guidelines to ensure the secure operation of medical devices. So the goal of our project is to develop a trust management framework to address the challenges in the medical device ecosystem, and we also aim to if we want to be more specific, we want to provide formal verification of the security protocols used for this framework, and to identify design time assurances that do not need to be attested during runtime. This would enable for a more targeted attestation of a specific set of system properties. So, about verification of security protocols, you might already know a bit from the previous presentations, but the goal is to prevent vulnerabilities, so to identify potential flaws before the deployment, ensure robustness, to guarantee protocols can withstand the attacks, in terms of compliance to meet industry standards and regulations, and trust to build confidence in the security measures. So let's talk about the formal verification techniques in security protocols. So the purpose would be to systematically discover these protocol flaws as previously mentioned, and this is an essential step in designing secure protocols. Examples of automated verification tools would be ProVerif, Tamarin, Citer, or VerifPal, as you could have seen earlier. Let's go a bit back to the basis. So what is a model? So model is an abstract representation used to simplify the complexity of software systems. In our context, we talk more about security protocol model, which is a framework that allows the description of security properties, but in greater detail and precision, considering also issues like beliefs of agent, time, and secrecy. Now, how can we verify security protocol models? So we chose two tools. First one is ProVerif, which is a cryptographic protocol verification tool. that can automatically analyze protocols for security flows, focusing on properties like secrecy and authentication, and it uses symbolic analysis techniques. On the other hand, we have Tamarin, which is a security protocol verification tool that employs automated error-improving techniques and helps with the analysis of complex protocols by ensuring their correctness and robustness through formal modeling and property proofs. For example, ProVerif is suitable for simpler authentication and secrecy checks. It is faster because it uses more aggressive abstraction, while Tamarin can naturally model stateful and mutable state, and it offers more precision, but is less scalable for large automatic proofs. In this scenario, we chose both Tamarin and ProVerif due to the combination of expressiveness, maturity, and active community support. As you've seen earlier, we are also using Dolevia authored model. Model is a powerful active network attacker. The attacker can intercept, modify, and delete any messages, and also inject new messages and impersonate participants. We assume perfect cryptography and no access to device internals, so the attacker cannot gain, for example, private keys or the memory from the actual device. And this focuses on protocol level of vulnerabilities and not on the implementation flows. But what are the challenges with these tools? So usually they require expert knowledge level. Both ProVerif and Tamarin require formal methods, expertise to model the protocols and interpret the results as well. These tools may not support all types of protocols or properties, and there could be scenarios where certain aspects of a protocol cannot be adequately modeled or verified using these tools. So we have to also keep this in mind. This is also a main reason that we are using two tools, because one can model and verify certain properties, while the other one is focused on other properties. So we can have a bigger surface of what properties we can verify. So how do we model the security protocols? We have here a flow, our flow. So we have here the formal verification component. First, we have the security requirements. We take this as input, and then the security protocol designs, which provide a security scheme, so descriptions of the protocols and also of diagrams. We verify this, and then the verification results are sent back to the security protocol design, so they can be improved if that is the case. And we also aim to extract the runtime verification properties. So what security properties we want and we need to verify during runtime to perform this process. So what was modeled so far by us, we focused on the extensible authentication protocol, on the enrollment of low-end devices and high-end devices, the generation of verifiable credentials, attribute keys issuance, and generation of attribute key credentials. What did we check in these protocols? So mutual authentication, also that the attacker must not be able to decrypt the sign-encrypted ciphertext or any other encrypted message. The attacker must not be able to compute also the attestation key or the attribute keys generated for proving attribute ownership by the intended holder of the verifiable credential. What are the results? The check process finishes in a short time because it can happen that the automatic verification tool does not, if the security protocol is too complex, might not converge, you cannot ensure that the security properties hold. Also, the design security schemes ensure that the security properties specified hold at design time. So how do we model these security protocols? So usually we receive the security protocols in natural language and in a sequence diagram that might have enough details to model the entire protocol. So this is an example of the enrollment for the high-end devices. So we create a sequence diagram in a tool-neutral notation based on the description of the security schemes in natural language and semi-formal and formal mathematical notations. So we can see here all the steps that each actor of the protocol does. Basically, here are the messages that are sent between the actors and also the functions that are used to compute certain attributes. We can see here in this example how we model the encryption in ProVerif. For example, here we have an abstract function of the encrypt, which takes basically the message, the policy, and the private key, a secret key, and returns the encrypted message, the ciphertext. Then, in order to be able to decrypt this encrypted message, then we need to define a reduction rule, which, when we apply it, so we disencrypt the ciphertext, we obtain the initial text if all the necessary criteria is met. Here is an example of other cryptographic functions modeled in ProVerif, how we abstracted them. So basically, for the key derivation function, where it takes input two parameters and returns a key. Also for derivation of policies and the public key. And here we have an example on how we are checking the certain security properties. Basically here the secrecy, which in this case we are checking the secrecy of these keys and properties. So we check if these are leaked on the public channels, while for this root key we check if the attacker can get a hold of it by either receiving it from a public channel or computing it using the information intercepted. And these last two are just to ensure that there is an actual path at the end of the protocol that it can be reached. There is a path that can reach the end of the protocol. Here we have an example of in order to be able to define to model these protocols for each actor, we need to define a process. This is an example of for the process of the device, where we model each step that the device needs to take. For example, as you've seen earlier in the sequence diagram, you can see here that the first message is an enrollment request, and it publishes on the public channel the public part of the root identity key. And these are the next steps that are used. For example, here to disencrypt the ciphertext, and so on. So what are actually the challenges here? So formal verification tools require expertise, as I mentioned earlier, and don't ensure correctness in the real implementations. Furthermore, there is no unified support for security verification across design time and runtime. So therefore, we try to find a solution for this, and we propose a domain-specific language that enables the protocol designers to model and verify their protocols without requiring the knowledge of multiple automatic verification tools. So basically, they can they model in a more friendlier way their security protocol design, their security protocol, and then we check it using multiple tools such as ProVerif and Tamarin in our case. How do we want to achieve this? First, we want to identify the most commonly verified security properties. So we do a literature review process where we search across multiple digital libraries. We define the protocol for this search, where we specify the search string and the criteria on the selection criteria. We focus mostly on papers with ProVerif and Tamarin models published in the last 3 years. So the goal is that each paper will provide a full Tamarin or ProVerif model, not only snippets, because then it's more difficult to make them run in a reasonable time. Then we want to extract and categorize the security properties. So we apply this analysis and categorization. We want to create a taxonomy of security properties that are modeled and verified in the past 3 years. We document both formal in first order logic and informal definitions, and we categorize the results based on the security properties. So we extract the protocol models, a representative protocol model for each security property. So basically, if we have for secrecy, we extract a model in both ProVerif and Tamarin that represents how secrecy property is modeled. We do this by extracting them from the existing studies or derive them from the selected papers. So the main goal for our domain-specific language is to create it based on the extracted models. We want to abstract away the complexity of modeling in ProVerif and Tamarin and simplify the security protocol verification process. We use this DSL to basically perform code translation from our DSL to Tamarin and ProVerif models. The goal is also to create notation close to the security engineers and provide a rich set of security properties as first-class language constructs, as well as global state modeling to support the global state modeling. So the results of the literature search are, in the end, we have 71 selected papers. As I mentioned, the paper must provide the ProVerif or Tamarin model. You can see here the search string. We are focusing on security, cryptographic, and protocol verification using Tamarin or ProVerif. The initial taxonomy, for this, we try to come up with the main security properties such as authentication, secrecy, privacy, access control, and integrity. And then we want to go a deeper level. So, for example, we split the secrecy in forward and backward secrecy, as well as the authentication. We have mutual, single-factor authentication, mutual, multi-factor authentication, and so on. So how do we plan to evaluate our DSL? So we are going to look into the expressivity of the DSL. So can users express all the necessary domain concepts? For this reason, we are going to also use our DSL to model the ENTRUST security protocols and assess its expressivity levels, and also create case studies, so to implement a real-world example to assess effectiveness. So as I mentioned earlier, we need to extract also the security properties that cannot be verified during design time and ensure that they hold at runtime. So why we want to prefer runtime verification? Because we ensure correctness, so we ensure security protocols are implemented correctly. We can do a pre-deployment check to validate the protocols before they go live. We'll see how this fits with our approach in a bit. Also conduct dynamic analysis, so we monitor and verify the implementation during execution. It offers adaptability, so to detect and respond to real-time issues, and they are efficient because they only use a single execution trace, in contrast to model checking where the entire state space is explored. So the proposed solution can be split into two parts. So we have something that some processes that happen at design time, and then we have runtime. So at design time, we have our domain-specific language that receives the security protocol and the security requirements. So we can see we have an example of the security protocol here with two actors that we model it. basically. So it's received here in the DSL, and we create a model of this that would look like this. So we define the functions that are used, the actors with where we provide them with the initial data that it's required in order to operate into that security protocol, and then we encode the messages that are sent between the actors, and that of course the functions used for computing different properties. Okay, then we have our model in our DSL. Then we create ProVerif and Tamarin models, so we generate them and run the verification. At this point, we'll have a result. If it's negative, of course, if the protocol has a problem, we'll have a result that looks like this, which is not that user-friendly, might be difficult to interpret by security protocol designers. And therefore, we want to use LLMs to interpret these results, so both for the output from ProVerif and Tamarin, and also generate hints or actual solutions on how the protocol can be improved. So therefore, the results, the interpretation of the LLM will go back to the security protocol, which they are updated, and then we have a feedback loop. At this point, we also aim to extract the runtime security properties and feed them to the runtime verification module. But in some cases, it might really be handy to have a pre-deployment check, either because the IoT environment that we want to test might be very big, and we do not have access to those devices, or it can be costly, simply it would cost too much. We want to emulate these devices, and therefore we want to deploy the actual IoT software on an emulation platform, start the security protocols, actually emulate also the security protocol simulation if you want to, and then apply the runtime verification on this. So this will ensure that once at the pre-deployment step, that all these security properties also hold, and then we can actually deploy our security protocols on the real environment. You might wonder why it's in this setup where we also have an actual entity. Actually, this is part of a digital twin. So we want to integrate the runtime verification module in a digital twin setup, and also use the emulation platform as a tool to also implement other digital twin services before deploying them on the actual entity. So, as I mentioned about the IoT emulation platform, we verify the implementation of the security protocols at the pre-deployment phase, and we plan to use this platform as a testbed for IoT environments. So what is the current status of all of this? So we created the taxonomy of security properties. The DSL so far supports the ProVerif translation for a variety of security properties. And we are currently exploring the LLM interpretation of verification results and also the runtime verification approach. As for the next steps, we want to add the Tamarin support to our domain-specific language and perform the entire process with the runtime verification using the emulation platform. For this, we want to start small. We want to define a use case and emulate the IoT environment, and then we apply the runtime verification on that, and from there we want to scale up to bigger setups. So I would like to thank you for your attention, and if you have any questions.
Thank you very much, Leonard. Thank you all for your participation. Now we move to the last and final session that you can pose questions to the speakers. Seems that there are no questions from the audience and the participants, so I would like to thank the speakers for their presence today in this webinar. The webinar has been recorded and will be available on the two projects' social media, the websites, and also we're going to circulate let's say the related material about all the series of the webinars. So we can proceed with the closing. I would like to thank the speakers for their presentations and their, let's say, clear way of presenting the formal verification concept and the aspects within the two projects. I would like also to thank the teams between the two projects from REWIRE and ENTRUST that collaborated for the performance and making tangible the series of the webinars for cybersecurity awareness. And last but not least, I would like to thank all the participants for this webinars, and I would like to thank you all for being present today here. And since there are no questions, we can proceed with the closing of the webinar and the meeting.